by Jesus Gomez. The goal of this experiment is to observe the motion of some object that is moving at the same speed without changing direction. So we're looking at the constant velocity of this object. In this experiment, I will also be using the physical principle of Newton's second law to observe the position and time changes of a ball moving at the same speed in a table. This experiment includes the analysis of the change in time versus position. The change of position is also known as the displacement. As a displacement, I will also create a model to compare to my analysis of the video on Tracker. I started this experiment by designing it based on the lab instructions. At first, I thought of filming the ball on the floor, but then I remembered that for the purposes of the video, it is better to film it on a shorter surface that is visible to measure. So the experiment is simple. I will push this ball over this table and see how it moves. So I also was able to make some measurements. The length of the table and also the circumference that gave me the diameter and also the radius of the ball. Let's look at the video. As you can see, the video is quite fast, and this will become important at the end and the conclusions. So some of the physical principles that are really important are Newton's second law, and here are some of the formulas that I'll be using on this experiment. So we started our analysis in Tracker, and here's our analysis of what happened in this video. See how I took a short part of the video that I thought it would be better to analyze. I managed to get some important data points from this experiment, from this analysis. Most importantly, these two at the beginning that managed to give me the initial velocity by using the formulas that I just gave you. I also took note of this final time because they will be useful for the computational model. Now, with this information, I was able to change some things on the computational model. For example, the radius of the ball. I also searched what is the average weight of a volleyball ball, which is 0.26 kilograms. I changed the ball position, which because it starts at the origin, so it would be 0,0,0 of a vector. And then the ball velocity, which is the vector minus 1.22,0,0. I calculated this by using the first two data points. So with the last time point, I also calculated delta t by dividing it over 100. And I used that on the while loop as the condition. Then in this part is where the physics really happen, because here I put those equations that I put you on the physical, those important equations that we will be using, which are the Newton's second law equations. So with this code, I was able to make this analysis. This model gave me some really important data points, which are here. With these data points, I was also able to make this graph. This graph in Excel is a comparison between the data points on the model data and the experiment data. As you can see, the model data is an underestimate of the experiment data, which is really rare considering that the ball is being affected by the gravity, the friction of the table, and other forces over it. But I think it's because of the time frame that I chose, and also the fact that it might be, and that time frame might be when the ball is accelerating. It might be it was a part where the ball was accelerating because it was too close to the beginning of the video. This means that it changed my estimate and make it too big. So as you can see, the experiment data doesn't fit the model data because the ball is accelerating, in this case to the negative side, but still accelerating. So what if I switch the axis? It would mean that this table, it would be on the other side, of the x-axis. So it would just be positive, and that's it. So we are assuming that the net force over the ball is zero. This doesn't mean that there is no interactions. There is the gravitational force interactions and the friction interactions. So in conclusion, we can use the momentum principle and Newton's second law to predict an object's position and velocity of a certain point. Net force equals zero does not mean that there are no interactions. We managed to create a computational model that takes in consideration the perfect conditions. We also observed how those conditions were not met in the real world.